So, the code which I am going to show you now, this particular code is using the Numerov algorithm to solve the one dimensional quantum mechanical simple harmonic oscillator. And so this code we will be using the bisection method to compute the energy, but we have purposefully not implemented or not make sure that the code gives us the correct asymptotic limits. This is done to just show you the effect that if you do not take care of the fact that the asymptotic limits of your solutions are correctly recognized by the code, then what might happen. So, this code is written by it is not written by me, but it is written by Professor Paolo Giannuzzi. So, I will just take you through the code. So, initially, as like all other Fortran codes, we have here the declaration of variables. So, basically this part is the declaration of variables. So, mesh gives me the mesh size, ICL is the index of my classical inversion points, then nodes gives the number of times the number of nodes I want in my solution, n cross is the number of times my solution crosses or changes sign, and then these are some temporary arrays. This is the array where I am storing the value of the potential at different values of x, that is half k x square. Then this contains the name of the output file. So, what the code first does is it asks the value of x max, that is up till what value of x or the maximum value of x till which we are going to do the integration, and the integration is done from minus x to x max to plus x max. But in reality we do only from 0 to x max, and then take either depending on the whether it is an even whether you want an even number of nodes or odd number of nodes, we make it symmetric or antisymmetric. Mesh is the number of grid points you want to do the integration on, and then using that we determine the grid size here. So, x max by mesh gives me the difference or the value of x between two consecutive grid points. We also allocate this local variables based on the mesh size. So, this quantity is my delta x square by 12, which we will be using several times. So, I have just calculated, I mean this has been calculated in the very beginning of the code here. Now, what this part of the code is doing is it is setting up the potential. So, my potential you know is half k x square. Here since we have used atomic unit as this reduced units, my k is 1. So, it is just half x square. So, what I do is I do the iterations from 0 to the mesh, that is the maximum points. Then I evaluate the value of x, which is I, and float, and I am converting it to floating point here. I is the index here into the dx, that will give me the value of x at the ith index, and once I know the value of x at the ith index, I get the value of the potential I, and that is given by half k x square. Then I ask the user, then this part of the code asks the user to support to give the name of the input file where or the output file where the data will be stored. Then this part it is the sort of the entry point for the new eigenvalue search. So, if you give a negative number of nodes, so the code will keep on doing it until and unless to come out of the code you need to give a negative value of the code, and if it is negative value then it deallocates and then comes out of the code. Okay. So, then what we are doing is we are setting up our E max and E min. So, this is E up is my upper limit or the maximum limit of the guess energy, and E LW is the lower limit, and this is given by the maximum value of the potential, that is half k m x max square, and the minimum value of the potential, which in this case is 0. So, once it does, then again here there is a brief sort of a detour here in this part of the code. So, the code automatically, if you do not give any initial guess of energy, what the code will do. So, that if your trial energy, if you set to 0, the code will start with the initial guess, which is the midpoint of E up and ELW, or else and it will keep on doing the bisection method till it finds the energy, or else if you just want to test for a single value of energy, you will you can give the input value of energy and the code will give the wave function. So, now here this is the main loop where the wave function is being constructed. So, this is my f at 0, that is at the beginning. This is this dx square delta x square by 12 into this potential, which we are using several times. Then what we do is we try to find out what is the classical point of inversion. So, in the beginning we set it to -1, and then we start the integration, start going over the whole mesh from I equals to 1 to the x max from, and at each point we calculate this quantity f I. Now, at the classical point of beyond the classical point of inversion, what will happen is this term will be so the f value will change sign. So, as long as your potential energy is less than the energy of for which you are finding out the solution, this term will be negative. The moment the potential energy is more than the energy for which you are finding the solution, this term will be positive. So, the product of these two will give this will change sign, and the point at where this change sign, the value of I at where this change sign, then this will give you the point of classical inversion. So, here he has also taken another care, that is the following, that sometimes it might happen that luckily you have this f I becomes exactly 0. Okay, then you will not be able to observe the sign. So, instead of because the way the sign is taken care of is it takes the product of these two functions and then it gives the sign. So, if it is 0, then you will not get this will not return any value, and so you will not be able to find out. So, what is done is, if it is exactly 0, this f I function, so what you do is you set it to a very small, very tiny non-zero value, so that you can do it. So, this loop basically what it does is it determines the value of I at which your inversion you go from the classically allowed region to the classically disallowed region. So, once you do, you also check that at which point how far the point at which this classical inversion is happening. So, how far is that from your maximum mesh size? So, if it is too close to the x max, then the last change of sign is too far, and then you do not do. That means something is wrong with that. So, you come out of the of it. But if that condition is not satisfied, that if things are fine, you move into the Numerov part of the algorithm, that is this part here. So, first what you do is you check for even and then odd number of nodes here, and based on that you set the initial conditions. If you have even number of nodes, then you set this one as the initial conditions, as we discussed. If you have odd number of nodes, then the solution is y at 0 is 0 and y 1 you take as x. Then you start the outward integration. So, this is where the outward integration is done, and then you also in this part, particularly in this region, you check whether your wave function changes sign or not. So, once that is decided, then you check whether the sign cross is the number of times the wave function is changing sign, whether it is more or equal to or less than the number of nodes you desire. If it is greater, then you replace your E up with the new with your guess value of E, the upper boundary of your bracketing region. So, you reduce the bracketing region, you go to the lower half, or if it is less than if the number of crossings is less than h nodes, you go to the upper half, then you set up the new trial value of E. So, you continue doing this till your difference between E up and E L W is greater than equal to is less than equal to minus 10. So, once it done, so here he has also so then you try to compute the norm of the function. So, this part of the code computes the norm of your wave function, and then also then your wave function is written in this file. So, basically what it he writes is the x value, the minus x value, the negative part of the wave function, and then so this is for the negative part of the wave function when x less than, for negative values of x, not the negative part of the wave function, I am sorry. So, this part is printing out the wave function for negative values of x, and this part for the positive values of x, and then it comes out. So, this is the program. So, let us run and see what we get. So, what we do is we compile it, G Fortran minus O harmonic 0 dot x. So, if we do ls minus ltr, we get it. So, let us try to run it. So, this is the so what I do is I type, say I want from 0 to x, or minus 10 to plus 10. I want 100 grid points for my wave function. I give the name of the output file. So, I am interested in finding out the ground state. So, I give the name of the output file as ground state out. So, in the simple harmonic oscillator, in the ground state we know that it has 0 nodes. So, I put 0. I want the code to decide the energy and all. So, this is what it has done. So, you see it converges after 39 iterations. After 39 bisection operations, it converges, and the ground state energy is half, we know, and it is very close to that. So, let us now plot the wave function and see what we get. So, if I do ls minus ltr, so this is the file where my wave function is plotted. The data for the wave function is written. So, it goes from minus 10 to plus 10. And so, the first column is my x, the second column is my wave function, which is y x, and then we are not interested as of now for the other 3 columns. So, we do not worry. So, we use, let us see how the wave functions look like. We use XM Grace. So, we go to as the plotting software. So, we go, so basically this is the file which contains the information and x y. Okay, and this is what we have. So, if you look at it, then one second, we just need the first graphs, not the others. Let me just okay. So, if you see that at x equals to minus 10 and plus 10, the wave function completely diverges. You would have expected it value close to 0, while in other case it is gone to a very large value. Now, let us try to zoom in and see how much what it looks like in the classically within the classically allowed region. So, we put x, and so the change the upper value of y, we put it to 1, and we apply this maybe 1.5. Yeah. So, you see for the ground state, what we expected is a symmetric Gaussian type wave function, which is centered at x equals to 0, and we get that. So, in the classically allowed regime, we see that the wave function, we get the correct behavior of the wave function, while in the classically forbidden regime, the wave function blows up. So, that highlights the necessity of the asymptotic wave function. So, if I take into account and do the corrections for the asymptotic term, which I am not going to show the code for you, I leave it for you to do, then and if I run it for the same wave function, if I use the same values, say 100 output file name A I give, and number of nodes I give 0, then I do a bisection search. See, it converges again at 39 after 39 iterations to a value of 0.5, and now let me plot it again. So, x m grace minus n x y a. If I plot it, so I have several things here. So, let me just keep the wave function and remove the others. So, what you see that this diverging behavior which we are getting earlier, that has disappeared now. So, that so through these two pieces of code, what we saw is how to numerically find the solutions of the Numerov's using Numerov's algorithm, the solutions of the one dimensional Schrodinger equation. And then we also saw how some of the difficulties of associated extra difficulties, I would say, associated with when you are trying to solve the quantum mechanical problem numerically.